A very good morning to one and all present here. If you can imagine it, you can achieve it. If you can dream it, you can become it. By William Arthur Ward. This inspiring quote in this pleasant morning, we welcome you all for today's session on MEMS sensors by Dr. Ashok Kumar Pandey, Associate Professor, Department of Mechanical and Aerospace Engineering, Indian Institute of Technology, Hyderabad, as a part of our 2-week certification course on MEMS, organized by Center for Micro Nano Design and Fabrication, CMNDF, in association with Department of Electronics and Communication Engineering, Savita Engineering College. Over to Dr. P. Shripriya, ma'am.
Good morning, one and all. This is Dr. Shripriya. I'm just going to give you a glimpse of our college and department. Savita Engineering College, established in the year 2001, an autonomous institution which follows the Finland-based education model, and we march towards less is more concept. College makes the students job ready by providing Industry 4.2 ready curriculum which imparts the 21st century skills. Project-based learning integrated with subjects improves the student skill set and makes our learners to be the best, which is the motto of our college. The Department of ECE was established in the year 2001. Our vision is to develop the department into the state-of-art Center of Excellence in Electronics and Communication Engineering education on par with global standards. The Department of ECE has well-experienced faculty of proven ability and diverse specialization. The faculty actively involves themselves in the research fields of MEMS, robotics, VLSI, image processing, and embedded systems. About CMNDF, the Center for Micro Nano Design and Fabrication was established in the year 2012. That brings the technology and applications of micro electromechanical systems, micro and nano fabrication, micro and nano electronics, electrochemical, 3D printing, bioengineering and processing, and computational modeling, together with researchers working on integrated circuit and system on chip design to create smart micro and nano systems. Labs associated with CMNDF or Savita MEMS Design Center in collaboration with IntelliSense USA, Wet Lab, Microfluidics Lab, Prototype Processing Lab, and the Nanosynthesis Lab. Under CMNDF, nearly 25 papers were published in reputed journals and organized international conferences and workshops in collaboration with the Department of ECE, Savita Engineering College. Presently, 4 members pursuing PhD under 3 CMNDF, and our team includes 10 researchers from various disciplines who focus to work with innovative thinking to bring up the groundbreaking achievements in the field of microfluidics, healthcare, and energy harvesting. Over to Nancy.
Thank you so much, ma'am. Now, I would request Mr. G. Dinesh Ram, Project Associate, Savita Engineering College, to introduce our guest of the day. Please, sir. Dinesh, sir.
Dinesh? Is he not there, Nancy?
Sir, can you unmute yourself?
Dinesh? I think he has some problem.
I do, ma'am.
Let me just introduce. Dr. Ashok Kumar Pandey is currently an associate professor in the Department of Mechanical Engineering at Indian Institute of Technology, Hyderabad. Before joining the institute, he completed his master's and PhD from Indian Institute of Bangalore and postdoc from Technion, Israel. He has worked in the area of design and characterization of MEMS structures based on linear and non-linear analysis of multiphysics since the last 10 years. Since the last 15 years. While he continues to work in this interesting area, which uncovers interesting physics, he has started working in vehicle dynamics to explore the application of MEMS-based sensors in controlling the performance and safety of conventional as well as autonomous vehicles. He has published over 50 journal papers and presented over 85 conferences, workshops, and invited talks in India and abroad. He has been awarded with Haythani Award 2010 by Society of Experimental Mechanics USA and Best Teaching Award in 2012 by IIT Hyderabad. We are very much privileged to welcome you, sir.
Thank you.
Yes, sir. We will now start our session.
So the session is yours, Ashok sir. You can get.
Okay. Thank you. Thank you very much for the invitation. And I'm really privileged to be here among all of you. So in today's session, I will be talking about the MEMS sensors, its design rules, and what are the difficulties that one can have during the fabrication. So the outline will be, as you might be knowing everything, but it's always better to start with very basic definitions. And then we will go into the different stages of MEMS development. And we will also talk about a little bit fabrication processes which are used in MEMS. Then how do we characterize these MEMS structures? What are the different components of MEMS modeling? And why there is a need for multi-physics and couple field modeling in this particular devices. And then I will demonstrate some of these modelings through some test structures. So as you all know, MEMS stand for micro electromechanical system and NAMS stand for nano electromechanical system. And the definition is because one of its feature is of micron or nano size. And in these structures, although there are different types of mechanism to actuate them, so if you're using electro, then we call it as a micro or nano electro. And when you actuate these structures, the mechanical component of this device get into the motion, and that's why we combine it as a micro electromechanical system which are fabricated on a single wafer. So in a formal definition, we define it as integration of mechanical elements, sensors, actuator, electronics on a common silicon substrate through micro or nano fabrication processes. And this is what calls for the analysis. This call for multi-domain analysis in dealing with the design of this particular devices. So what are MEMS? Whether we can use it as a sensors or actuators? So yes, so MEMS can be used as a sensors. And what is sensor? Sensors are developed to measure physical quantities, and actuators are developed to induce the effect. So for example, there are actuators which will actuate the motion, and sensors, it will sense some of the changes which is happening outside. Okay, so examples means what really happens when there is transfer of energy from mechanical to electrical, so we call it as a sensors. Okay, and when there is a transfer of energy from electrical to mechanical, we call it as an actuator. So that is one way of defining the difference between sensors and actuators. And this is how basically you can make use of MEMS for both the things. So what are those mechanical energy? In what form they may exist? They may exist in the form of displacement, velocity, acceleration, force, pressure, and temperature. So these are your mechanical parameters that you can have. And change in any of these quantities will bring change in terms of the measuring quantity, which are current, voltage, capacitance, resistance, inductance, etc. What are the examples? Examples may be inertial sensors, accelerometers, gyroscopes, pressure sensors, gas mass sensors, temperature, humidity sensors, force sensors. Similarly, we have actuators, for example, micromirrors. So projectors which we use for presentation, they consist of many micromirrors. And then we all talk about RF switches, micro relays, and then thermal biform, comb drive. These are all actuators, and that's how we can like define it. So what are the things, what are the facilities which are used for fabricating these devices or characterizing these devices? So here you can see there are some fabrication related equipments, which are some of them are there in I have shown just few of them over here in this slide, which are there at IIT Hyderabad. And these are scattered around different labs and departments. And now we are going to have a nano facility under which most of them will be under one umbrella. And similarly, there is a characterization facility, electrical, mechanical, material characterization. So these are, so you require all these to first fabricate it and then do the measurement to see whether your design really works properly or not. Okay. So what do you really get into a design? So basically there are two types of devices. One is called static devices, another one is called dynamic devices. So we will talk mostly about the dynamic kind of sensors. So how do you characterize those dynamics kind of sensors? So dynamic types of sensors are basically characterized by the frequency. So for that you can have one vibrometers. So let us say there is uh, uh, let us say there is a uh, yeah, so there is a MEMS structure, and when the laser light from here, so this is your laser, and when it goes this side, it falls here, and we have a device which is kept here. So when it falls over here, so your and of course you will have to excite them through electrical means. So in that case, you will have actuation of these structures, and you can measure the response corresponding to a given frequency. So this is what we mean by the dynamic. So dynamic sensors, in dynamic sensors also we subdivide into these structure in these devices into resonant sensors. So resonant sensors are sensors which operate near the resonance. And advantage of operating these resonant sensors near the resonance is because for a small excitation you can have a very large displacement, and when there is a large displacement there will be large change in capacitance or other electrical quantity which you are going to measure. So this is another kind of device. So this is one single, you can just put it into an array of them, and then you can excite them, and all of them are having certain advantage, certain desired output into the mind. So this is how basically we characterize them. So when we look at some of the commercial MEMS project, the first thing that comes into our mind is MEMS accelerometers, right? Because you will see that in almost all the cars we are using airbag, and the airbag uses these MEMS accelerometers, and mainly by the analog devices. And this was the first device that came into the market uh, uh, like initially, and after that there were many devices that started coming with the progress of and standardization of the fabrication steps. So how it works, and one more thing you will have to really look here, if this is the whole device, you will see that only this small portion is being occupied by our MEMS. So it means that only the mechanical component, which is movable in nature, occupies only a small step. Other than this, you require a lot of electrical circuits for reducing the noise, for or amplifying the signal, so that you can get the response in which you can measure through your instruments. So here you can see there is this is your two axis accelerometer. In one of the axes, if you try to see this, here you have a proof mass which is suspended by beams here, 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 and here. So when there is an let us say there is an acceleration which is applied. So when acceleration is applied, your proof mass will go into the opposite direction because of uh, uh, D'Alembert principle, right? And that way your structure will move in the opposite direction. So when it moves in the opposite direction, you can see that there is a static structure which is on the sideway of this proof mass that will also move, and it will move towards one of the electrodes, resulting in the difference in the capacitance between these fixed electrodes and the moving electrodes. So when you try to measure capacitance change because of the motion of this structure, which is moving because of change in the acceleration, so we correlate the acceleration change with the capacitance change over here. Okay, so this is how basically the transformation happens in a MEMS accelerometer. And similarly, you can see there are many MEMS pressure sensors. And again, I would like to bring your focus over here that this is the only reason where your MEMS device is located. Rest of them are all electronic signal conditioning circuits that you really see. And then MEMS microphone is another very vastly used example, which are used by many people. And MEMS gyroscope, which is even more, starting from toys to our phone to different cameras in laptops. So you will see that MEMS gyroscopes are really very, very important. Now, what are the different types of MEMS gyroscopes, and why? You will see that the toys, cameras, and all, they may require some medium range gyroscopes. Means uh, they may be okay if they are able to measure like angular motion with certain error. But when you are trying to measure some precision angular motion or rotation, you require different types of gyroscopes. So first, so here you will see that this is your conventional MEMS gyroscopes, which are having combs and proof masses. And there are two proof masses here. You can see this is one, this is another. And when they move in plane, so they may move in phase, and then they may move also out of phase. So one is called drive direction, another one is called sense direction. And when there is a rotation which is provided along this axis, so you will see that when it moves up, that will give you a sense output. Okay, so this is one type of gyroscope. And another kind of gyroscope is your shell gyroscopes, then disk gyroscopes, which people are exploring to improve the characteristics of these gyroscopes. Right now, when you try to see one of these devices which are completely integrated, you will see that, as I said, nowadays people are trying to put a lot of these sensors on a single platform. So here you can just see this is accelerometer, this is gyroscopes, magnetometer, barometer, here your connectors and all of them are there on a single platform, right? And this is the advantage. That's why we are really going towards we have been investing a lot of time since a couple of decades just to get sensitive sensors and with reduced size, so that we can put many of them on a single platform. So these are the specifications that I don't need to really go into. Now, if you try to see the biggest application, of course the application is there in aerospace, in many of them, but the biggest application that we can find is in vehicle, which is accepted by everybody, you know. So in this case, you can have application in terms of airbag that I told that they use accelerometers. You can have pressure flow sensors, you can have inertial sensors, you have micro scanners, IR sensors, RF switches, temperature and pressure sensor in the tire, you know. So there are many of them which can be used, and you know, BMW 740i has already used 70 such MEMS sensors in the development of their cars, starting from anti-locking braking, active suspension, appliance, navigation, vibration, fuel sensors, noise reduction, you know. So these are some of the application that you see. Now going into a little bit more inside of these applications, you will see that in automobile you can have a sensors which are associated with, you know, dealing with the harsh environment, then steerings, then safety, you know. So these are, and most of these things are divided into 4 different parts. One is your safety and convenience, so you will have to find out sensors which are associated with safety and convenience. Now the sensors which are required for controlling the powertrain of your automobile, then for body electronics, you know, then also you will have to improve on the sensor design related with the driver information. Sometimes you will see that most of the accidents happen when driver falls asleep, or you know, he is unconscious in some different in cases. So there should be some kind of alarm with the help of these sensors which can prevent you know, the accidents of that nature. So this is how basically people have started, you know, classifying and trying to figure out which kind of sensors can be used for improving the different mechanism under these classifications. And if you see, you know, a typical unit electronics unit is the unit which will handle all the sensors in the, let us say, in your automobile. Now you will have that there are circuits which will deal with different sensors which is related with your, you know, drivers, then analog circuits. So you, looks like, you know, it has to really work so much, it has to process the signal so fast. Now what is the point? Like, we are trying to increase the number of sensors, but we are using the same kind of electronic circuit. So is there a way we can improve the processing of these electronic circuits also? Now in addition to that, if you simply look at, you know, one engine, there is like lot of sensors are being used or about to be used. For example, here you have MEF sensor, throttle control sensors. You know, you take a point everywhere, you know, you need. So just the engine part of the whole vehicle itself needs such kind of sensors, you know. And similarly, you can see the diesel engine where you will have position sensor, pressure pump where you will have to measure the flow rate, you know, temperature sensors, pressure sensors. So at different location you require many, you know, thousands of sensors all around. So the question is, just, you know, for example, for engine control unit, the electronics which controls this engine, you see that sensors can be of throttle positioning, intact air, manifold, mass, fuel, in cylinder, and all that. And similarly, actuators can be associated with all these activity. Now it has to, just this response circuit needs to really control, and if there is a delay, you know, time delay related with the processing of these signals of the sensors or actuators, you know, there will always be some kind of error, you know, there will always be some kind of performance loss, you know. So what is required? So, and so these are the things which are there with the conventional, you know, automobile. But since we are talking about this smart car, autonomous cars, so it means it's saying that you have to again improve the number of sensors right? So here you can just see, when you talk about smart cars or autonomous cars, you need to really talk about many things around it. Now, how you're going to really measure it? You're going to use camera, you are going to use a laser, you're going to use uh, other different types of sensors, and it has to be processed so fast, because if you are driving at a high speed, so everything needs to be in that order. So here the question is, it's not about sensors design. Here is a question is also about the processing of those signals which are coming from different sensors, and should decide accurately what it needs to be done. Otherwise the whole concept of smart car or autonomous cars will really fail. And that's why you see there are a lot of tests that are being going on. Even if many companies have developed these autonomous cars, they are not really going to take it out in the road, because of these problem. So here, for this you need to care about safety concern, powertrains, body electronics, driver information. These are the things that I was talking about. So it means there are too much of sensors and actuators, too much of signals, video signals, optical signals, radar signal, and different sensors, actuator. So how to handle so much of data at fast rate? So either you should design low powered and fast sensors actuator, or you design a different electronics based on uh, uh, the fast mechanism. So here optical is very accurate. Radar can go for a larger distance. So if you combine both of them, it's called lidar, which will measure with the approximately same accuracy of optics, and can measure for a longer distance, so that it can, that's why lidar is being used in the autonomous cars. So these are some of the examples where you can just see a car needs to get these signals. So what is the outcome? The fast and low power sensors and actuator we need, and also fast electronics. And that's why there is a, like, it's not now, but I think it's from last 7 to 8 years, even 10 years I would say, people started talking about the optoelectronic circuits, right? So that they can increase, and they are forming optical cavity, so that the processing of information can be done at a faster rate, that is at the quantum rate. That is the ultimate limit, quantum limit, right? So quantum electronics we are talking about. So how you are talking about quantum computing, quantum electronics and all that, but unless your gates, quantum gates are formed, you can't really do it. So what is the way, what is the, like, how you are going to form it? So that's based on your optical electronics circuits, and making use of optical cavity. Now coming into another application, very interesting application, is called the flexible electronics and the MEMS integration. So until now we saw the size of MEMS structures are quite small, so it is fabricated on silicon wafers, right? So but how to make use of it for a larger structure? So the people started making use of this flexible electronics. Okay, so the examples are like, you can use it in smart clothing, you can use in lightweight military devices, integrated health monitors, bendable solar materials and all that. So this is a field that cannot be made small, but must be big in order to interact with big things. For example, let us say if you want to have the conditioning structure, health monitoring of your car body while you are driving. Now how you will come to know that some of the portion is getting more stress, is about to break? So if you are having these kind of sensors, you can simply put it on the surface of your car body, and it can tell you immediately what is the like many information, not just one. It can give you many information. So that's why the advantage is that it can also conform to surfaces, so that it can impact wide range of applications. And this is a typical device that you can see. And the advantage is that you can band it in whatever orders. Okay, so it can still work, and there have been a lot of work, lot of work that uh, that uh, that has been done, and the people have started using it. Another application you can see, you can monitor your health with these flexible electronic devices. And you have a sensors, temperature sensors, let us say. You can measure your blood pressure and all. Many things you can measure. Similarly, you can take it as a watch. Your eye, uh, you can put it on your eye. You can have a temperature monitoring. So these are some of the interesting examples or applications where you can use all these small. Here you can see these devices are very small, and they are just into the flexible platform, so that you can use it properly. Then after that, there is another very interesting applications that is coming related with metamaterials for terahertz electronics. Why terahertz electronics? If you see, this particular wavelength, it is divided into these three domains. So in these wavelength, from 1 centimeter to 1 meter, we talk about microwave electronics, and the frequency will be in this range. Okay. Similarly, for infrared, that we know, that talks from 100 micrometer to 1 micrometer, and the frequency is 10 terahertz and above. Now there is a reason which are being unexplored because of the difficulty in analyzing this or controlling it, which is called as terahertz regime. All right. So in microelectronics, this is the very conventional electronics happens over here that we study, and the application is wireless communication and radars. Infrared, here we are talking about optical fiber related communication or changes that or the devices which fall under this reason. And in terahertz, as I said, there had been moderate progress in sources and detectors and functional devices such as this, which do not exist. So because if the devices doesn't exist, you can't really make use of this particular reason for the application. So if you just try to see the application over here, so means 1 terahertz, and here we are talking about 300 micrometer wavelength range. These are some of the things that we'll have to keep in mind. Then I will talk about which kind of device can be really very useful to work into this particular domain. So before emphasizing this particular field, we should know why terahertz. Terahertz because it is non-ionizing and safe to use on humans. Second, it is ultra fast communication. We were talking about how to really increase the processing of signal of a different electronics. So this is another terahertz. If you try to operate a device into terahertz regime, you can make the communication faster. And third advantage is it could penetrate many visually opaque materials. Okay, and it can also be used for screening for security and biological imaging. Now coming to metamaterials, so I talked about terahertz. Okay, second, what is metamaterial? Metamaterial is artificial structural materials with controllable electromagnetic properties. What are electromagnetic properties? Permittivity, permeability, your conductivity and all that at desired frequency. Now there are three different examples here. If your permittivity is less than 0, we call it a cut wire structured plasma. If permeability is less than 0, split ring kind of resonators we use. And N, which is the refractive index, if it's less than 0, then composite metamaterials, this is what we talk about, with where both epsilon and mu exist at the same frequency. So the biggest advantage of terahertz metamaterials is that metamaterials which can be tuned to desired electromagnetic properties And it is also found that the size of these terahertz metamaterials is a perfect match for microfabrication techniques. So the MEMS can be used for, creating such kind of terahertz metamaterials devices. Okay. Now going into some more interesting aspect of it, that if you see, to explain it a little bit more fundamentally, so if you see a material can be regarded as an effective medium characterized by a complex electrical permittivity. Okay, and if you see this, it has a real component and imaginary component, and similarly complex permeability, which is associated with your real and imaginary. So you have electromagnetic, both kind of properties which have to be controlled. And but most of the time what really happens when we make when we select a device, it has a fixed electrical permittivity and magnetic permeability, right? But in metamaterials you can attain the desired permittivity and permeability. This is what is the advantage of working in these kind of materials. So you will see that there are a lot of research that have been done in understanding these real parts of permittivity or permeability to create. Okay, so what needs to be done is we need to understand this imaginary component which is associated with the losses. Okay, now sometimes losses are good, sometimes losses are bad. So for many applications such as perfect absorber, you will like to maximize the losses. Okay, so but why do you need those kinds of material? You need those kind of material so that you can do yourself like this, right? You can put these material on your face and you will become Mr. India. And similarly, you can put it on your body, you will become like your bodiless. And if you put it like this, so all the range of different metamaterial kind of structures that you can have. So metamaterials can be easily tuned to desired electromagnetic properties. And the size of, as I said, this terahertz material is a perfect match for microfabrication techniques. So here, if you just look at the metamaterials are sub-wavelength structures in array form. So the question is how it looks like. What do you mean by tuning the properties of these metamaterials? Is it one or it is an array? So basically metamaterials exist in arrays form. Now the question is, what is the size of one of these material? So that will decide the size of the wavelength. Okay, so 1 terahertz corresponds to 300 microns, and MEMS devices can be fabricated of that particular size. So one example of metamaterial, terahertz metamaterial, you can see like this. Okay, there are many of, so this is one substructure, and when you use it for many of them, it become array of these structures, and together it gives you the property of a single metamaterial. Okay, and what it does, it helps. And what is the size of this? So here you can just see the size, right? The size will be between within your like wavelength of terahertz. So what it does, it can control the transmission and reflection of light. This one property by tuning the electro and magnetic properties of these structures. Okay, so this is the biggest advantage of such kind of metamaterials, MEMS devices. Okay, now when you deal with array of these structures, this is another biggest example. So you have one single element, you have array of element which is little less, you can have many of them together. Now how are you going to, because all these devices have to be bonded on substrate, right? Or one die. So to interface these devices with electronics, there are different types of integration mechanism exist. One, like you make your devices on one die, you make your electrical circuits on another die, combine them using wire bonding, right? So what is the disadvantage of this? You will have parasitic capacitance, okay, and that will reduce the noise. Another one is you make CMOS and MEMS, just club them together like this, right? So these are called monolithic kind of approach. And one can also do a little bit of more smart, integration of this CMOS circuitry and your MEMS device which is hanging over here. So this is the case when your device is passive. Passive means static, okay? But here the device has to move, so it means it has to be hanging between the electronics and your this substrate, right? Because the device is hanging on its substrate, so when it is going to combine with the electronics, one can have some kind of via through it, and then you can seal it to create the required vacuum in the chamber. And vacuum is another important thing which is required, because vacuum can induce damping, gases can induce damping of your structure, and I will talk about when you deal with the performance of these devices, damping plays a major role. Okay, so hybrid type, monolithic type, heterogeneous type, and advantages are like system on chip integration can be done, and these are many of the advantages that you come across. Another example, these micromirrors. You can see this is one unit, and here there are many of them, right? So they have to be again bonded together. So these are the steps that we follow. You have a silicon wafer, SOI wafer, and then you have IC wafer. You first do some, you glue it, then try to take it out through the etching process, then make a hole here, and then put some metallization to get the circuits, and then you put get rid of this glue to get the hanged structures which are formed together, so here you can see circuit is formed immediately through this. You don't need to do any kind of wire bonding. So this is how you try to form a integrated MEMS sensors. Okay, another example is to get the low noise electronics is to uh, develop carbon based field effective transistors. So here this is your drain, this is your source, and in between you try to put the carbon nanotube, so which can be used, which can used for detecting the viruses or biomolecules over here. Then one can also, instead of carbon nanotube here, you can also make use of spin related transistor. So if the spin changes, it will be in one case it is on, another case it is off. So by changing the spin, so why we are going into these small details? Because we want to measure lowest signal through these devices, and these lowest signals are will come only from these viruses or noise and all that. Okay, so and another thing is you can go to the quantum regime only when you can suppress the noise. Okay, so when you go into these devices, it is really required that we should be able to design these kind of sensitive electronic or transistors or sensors. Another such example is the biomolecules. Okay, so that's why between these two, source and drain, so this is called the molecular transistors. So you will see that there are a lot of devices. You just take a thing, and the people are coming with a different types of this transistor, MEMS based transistors. Okay, and this finally, this optomechanical cavity based devices. So which to increase, of course, to increase the signal rating, right? So as I was talking about, when you have so much of sensors, you need to also improve the logic gates, right? You have to improve your electrical processing. So for that, unless you improve these electronic devices, you can't really do it. So that's why people started talking about optomechanical cavity, where the laser light. So let us say what really happens here. Here you can see this is, let us say, a fixed uh, glass or mirror, and this is your moving mirror, which is related with the MEMS. Okay, so when it vibrates, what will happen? Your standing wave will be formed here. So when the standing wave is formed here, so you put a laser light, so some of the wave will pass through it, and it will get trapped between, if this one is of the order of the wavelength of your laser light, your standing wave will form over here. Okay, and then a small movement, it will just start interacting. So this mechanical thing will start interacting with the optical wave. Okay, so that's why we call it as a optomechanical mechanical effect or cavity, and this is called the optomechanical cavity. Now people have formed different types of cavity. One is here, you can see the small disc type, which is erecting on a small post. So if you put a laser light like this, let us say this is your laser, and if you put it like this, so what will happen? The cavity will be formed between this upper one and bottom, and when your upper structure vibrates, this cavity will also oscillate and will couple with your mechanical structure. Okay, and it has unique effect. It has a unique effect. Now the motion of these structures can be of different mode. So let us say if this is one mode and this is different modes, here you can see. So that way your uh, optical wave will also, standing wave is formed, that will also interact in a different way. Okay, so these are the example. These are some of the like numbers that you can see how these devices are. So this is your, one can see that this is like a bulb kind of structure, which is shell kind of structures. This is your planar beam. This is your ring type. So different types of cavities are formed for different purposes, and of course to attain different frequencies. Okay, so here you can see the range of frequencies are quite different, and what is really required, one of the requirement is that quality factor should be very high, means damping should be very low. So we discussed about all this, so many applications and so many things over here, but how do we understand their design through the fundamentals? Okay, so until now we were just talking about the applications, different sensors. Now let us go into the more fundamental approach. When you have to develop a MEMS, what is really required? You have to first think about what is the function that you want to measure. Means whether you want to go for temperature sensor, pressure sensors, inertial sensor, means so related with that change, you will have to find out what dimension need to be taken. Okay, so after you design, after you are done with your design stage, you go into fabrication stage. Now depends on whether you are going for a thick micro devices or thin micro devices, you choose your fabrication type. So there are different types of fabrication. I have mentioned few of them here. So surface micro machining, if you want to just measure a thin and planar structure, so you can use surface micro machining. Bulk micro machining can be even used for a little bit more thicker structures, and here you have layer wise layer deposition and etching which goes on, and in bulk you try to create a structure out of the given die, okay, by machining it. And Liga process are used for even developing even more thick structures like micro motor, right? Micro gears which are quite thick. So you have to make use of some very specialized fabrication technique in that case. After doing that, you have to do, wafer level testing, of course, before going for the packaging and all. And what it does, it ensures that your fabrication is standardized and the MEMS structures are released properly. But after the standardization is done, you don't really need to do this all and again. For the usually it is not part of the commercialized cycle. Then you go for packaging, development of custom packaging. So for different devices, packaging has to be decided, because some of them will work at ambient pressure, some of them will work at vacuum, some of them will work at a very high temperature, less low pressure and all that. So you really need to devise your packaging. This is another challenging part. That's why we can't really make use of MEMS in everywhere, because it fails. If it works for one application, it fails for another, because it may be compatible, its design may be reliable to that level, but the lack of reliable packaging makes the device fail. Okay, so this is another area where we need to really focus a lot. Then we do testing of some of the packaged device to ensure that everything comes back. And when you okay, and when we deal with CMOS MEMS integration, so here we have the coupling of the fabrication and packaging with go together. Okay, so this is another advantage why we also talk about this CMOS and MEMS integration, and it's a very important role to play in the development of different types of packaged MEMS structure. All right, so just to give a very small overview of what is surface micromachining. So it involves addition of thin layer on the substrate, and when you try to fabricate a simple structure, you start with a substrate, okay, and deposit some layer here, and then you do patterning, right? And after that you do etching. So here you can see your sacrificial layer is usually oxide or nitride, okay, and then you do patterning either. So there are two different way of doing patterning. Either you do using e-beam lithography, or you use it using photolithography, right? And after that you do etching. Now etching is another biggest area. After you transfer the pattern, you should make sure that you have etching, desired etching. Otherwise what will happen, there will be some more etching in this direction, more etching upward. So based on the type of devices, you have to look for the etchant which will do either isotropic etching, anisotropic etching, and based on that, different types of etchants has to be used. Most popular etchants are KOH, TMAH. These are in combination of NS2OH also is being combined to increase the rate of these etchants and all. And so after this, you remove this photoresist that you have put, and then you put your metal. You do deposition of the metal through thermal evaporation after RF sputtering, electron beam deposition. There are different types of this metal deposition instruments are there. And after that you remove this sacrificial layer, this one. So when you remove, you can see that there will be a hanging microstructure, and which is fixed to your substrate. And of course there will be some insulation over here, okay, so that it doesn't really do short circuit when you apply signal between this and this. Okay, so that way you have created the structure, complete structure. So how you started, the substrate with a sacrificial layer which is oxidized or nitride, then you put photoresist and transfer the pattern, and then you do etching, right, you with the help of required etchant. And after that you get rid of your photoresist, then transfer the pattern, deposit the metal layer on the top, and then get rid of this sacrificial layer, to get the hanging structure. Now when you are done with this step, you may get a different types of structure. So here you can see some of the beam is straight, some of the beam is deflecting upward, right? So what to do with them, why it is coming? So they come because of the residual stresses. Okay, banding is due to residual stresses. So these are the things that we have to keep it in mind. Now what happens in bulk micro machining? It involves removal, it removes part from the bulk. Okay, so for example, let us say you are having silicon oxide, okay, and you have transferred the pattern. Now etching will start from the bulk only, you are not depositing any layer. So in this case you use KOH. So when you use KOH, you can see that from here it is all etched, but there is a part under the beam which is left out. Okay, so if you see it from the top, it will look like this. Similarly, if you use this one with another etchant which is called TMAH, so you can see this at least the material underneath is completely gone, although it has the slanting edge on the sideways. Okay, so that will look like this. So in this particular case, if you just try to see the example of these two structures, you can see that the importance of selecting perfect or correct etchant is really required to get desired or to get a good microstructure. Okay, third one, wafer bonding. So in this case what you do, you take two die, you create a cavity over here, okay, and then bond them together. So when you do bonding and then you get rid of the top structure, pattern it and create the structure. So get rid of, you etch the top layer, then pattern it and then do etching. So here when you do etching, so what will happen? You will have a structure. So this can give you little thicker, beams, and which is of importance using this particular method. Okay. So these are some of the badly fabricated structure. It's not badly, I would say that, but sometimes when you don't really follow uh, the fabrication rules in designing, this is what really happens. So let us say in this structure here, you can see this part is quite wider than this. So by the time it etch this part, it won't be able to take out the part underneath here, right? Similarly here, this one is designed so long, and also this stiffness of this beam is not strong enough to pull it up. So what is happening is the end part is sticking to the bottom layer. Okay, so this is how basically, but you can take it out using different trial and error, like drying it up for some time and then vibrating it ultrasonically. So there are different ways you can help, but still if you don't follow the design rule of such kind of things are regular results that you really get when you fabricate your structure without thinking about the design. And yes, there are different software, different tools, for example IntelliSuite and Coventerware. These two are major player who have modules related with the fabrication of these structures. So you don't really require so much of this equipment that I was showing you in the beginning. It requires crores of investments to really get it. So it's better if you are focusing on fabrication technique. So here you can just see that, I will just play one video here. Oh, so it looks like I'm not able to play it. Hmm. Yeah, so here you can see, right? So there is a deposition, then patterning, then etching, and you get a structure. So if you whatever I told you in surface micro machining, if you follow those steps in this particular softwares, you will get, these structures coming out. Similarly, you can get all of them fabricated like this. So after following these fabrication steps, you will develop a structure automatically, okay, and you can do the analysis of those structures basically for the analysis, whether it will be used for pressure sensors or temperature sensors, or for the type of sensors that you are looking for. All right, so this is one software. So now up to now we were talking about the fabrication. Now let us look at the operation of one of these devices. Okay, so here let us say you want to uh, operate one device. The middle part you can see is a proof mass, which is suspended by four beams over here. So if you apply electric voltage between the bottom electrode, so this one is the bottom electrode, and this one is associated with the hanging beam. Okay, so when you apply the signal in terms of DC plus AC, here you will get oscillation like this. Okay, so this is how basically your micro device will work. And if you are doing wafer level testing, you can use laser. Okay, so in this particular, so this is what I told, that you are exciting between these and this, and when you will have to do the measurement, you put the laser light, and then because of the shift uh, in the displacement, because of displacement of this particular structure, you will have a Doppler effect, and that Doppler effect will give you the change in the displacement through the displacement decoder, velocity decoder, and accelerometer decoder, which are there in vibrometer. Okay, so from here what you really get, because of the vibration of these structures, from here you will get the vibration of structures, the mechanical effect, electrical effect, optomechanical effect, right? So what is this mechanical related effect? What is the quantity which you are looking for as a sensor and actuator? So here these are some of the devices you can see here. Okay, this is your MEMS microphone, this is MEMS torsion mirror, this is MEMS cantilever, now this is vibrometer. Okay, here you can see, if you excite, you will get a motion like this. Here if you see excite, you will get torsional motion like this. Here if you excite, you get cantilever motion, right? So it means when you try to see the motion of these structures, the all of them are oscillating at a resonance. Okay, so from this device and from these structures, we try to look at the resonance of these structures, and the resonance of these structures are captured using these FRFs, right? So if you see this peak, this will give you first mode of motion. It means that this cantilever, this fixed end will be 0, and the free end will move like at the maximum amplitude in the first mode. But when you go to the second mode, the motion shape will be like this. Okay, third mode will be like this. So as you go into different frequencies, you are having different types of displacement form, and all of them happened at different frequencies. So here you can see it has a different frequency, here it is having different, here it is different. So it means that when we try to design resonant sensors, we have to look at these peaks, like where we want to really operate. Okay, so in this particular MEMS cantilever beam. The first frequency appears as 43 kilohertz, and second one appears as 245 hertz, and third one appears as 690 hertz. So from these peaks, what are the design parameter you have to really look for? So first thing that you have to really look for is the frequency, which is associated with Km, under root K by M. So K is what? Stiffness of this hanging structure. M is the mass of this hanging structure, and this is called damping ratio, which is C by Cc. Cc is critical damping, and damping is governed by how wide this particular peak is. So the frequency related with the peak is called your this frequency, natural frequency, or resonance frequency in case of forced vibration, and damping ratio will be associated with quality factor like 1 by 2 zeta, right? So quality factor says how sharp is your peak. So if Q is very high, means damping is less, it means peak will be very sharp, right? And similarly, if Q is less, damping is more, this will be wider. Okay, so resonance devices, MEMS based resonant devices completely depends on how you are dealing with this resonance peak. Okay, whether it is thin, whether it is in the gigahertz, megahertz, or kilohertz range. Whether you want wider peak, it means you have to put more damping. If you want lesser peak, you need to have very small damping so that it become very thin. Okay, so this is what we try to control as a designer, before we fabricate our device. So how do we really look for example, let us say we take a cantilever, micro cantilever beam. We can divide them into the lumped parameters like effective mass, effective damping, effective viscous damping, and effective linear damping. Okay, and this is your forcing, harmonic forcing. In that case, we can write spring mass damper system equation like this. And M, so in this case, the important thing is this M is different from the total mass M. Okay, so M is the total mass, which is mass of the beam. So in the first mode, I was talking when your free end reaches the maxima, and this is 0, and you don't have a first mode. So in that case, you will see that this M, which is called the effective mass of the beam, which is participating in the first mode motion, is only 0.24 times the total mass of the beam. Okay, similarly, we try to find effective stiffness. So for cantilever, it is 3 EI by L cube. E is the Young's modulus, L is the length, I is the area moment of inertia, which is BH cube by 12, right? So if you see that, this is what you are going to get. So you are done with M effective, K effective, and similarly C effective. So damping due to the structural damping, fluid damping, support losses, or different types of losses that exist. So you have to combine them and put it into C. And remember that all of them should be like the equivalent viscous damping, okay, damping coefficient. So when you are done finding out these parameters, you simply have to substitute it here. So after that, you substitute it into here. If you put K here, M here, you will get your frequency, right? So this frequency should be closer to your experimental frequency. And similarly, damping, you will have to find out this total C, and this Cc is nothing but 2 under root Km, and K, you know, it is here, M here. So it means you will be able to find out damping ratio also. After that, quality factor, which is nothing but 1 by 2 damping ratio. Okay, so all these parameters you can find out for a cantilever beam if you are able to find these 3 parameters. Okay, and once you are done with the calculation of frequency and quality factor, you will be able to define the sensitivity and the performance of your MEMS devices, which is characterized by, so sensitivity means very sharp. It should be able to give you smallest change which is possible. Okay, so unless your peak is very sharp, you will not be able to get a very sensitive device. So that's why we try to reduce the damping to have a sharper peak, so that sensitivity can be increased. But on the other hand, we also need to get the higher bandwidth. So bandwidth can be through this or by moving your peaks over a given range. Okay, so they all of them, so it means that performance of a MEMS device is measured by types and strength of excitation, frequency of the system, non-linearity in the system. We have not dealt with non-linearity yet, but since these are very small device, the deflection may cross maybe beyond the thickness of this device. So when it is beyond the thickness of this device, then the non-linearity may become evident. Okay, so we have to include those effects also. And then damping, of course, different types of damping which exist here. So what are the modeling challenges for the MEMS devices that we really look for? So the modeling challenges are non-linearities. In that there may be non-linearity associated with forcing, which is excitation in capillary forces. Sometimes when your device is coming closer to the substrate, you will see that what will happen, there will be some fluid, so capillary force will be formed, and that will create another kind of opposite force. Then damping, non-linearity in damping, which is associated with your squeeze film and other. Stiffness related, geometric non-linearity, like this here you can see there is a large stretching of this. It means that it will simply go into the geometric non-linearity, right? Then material non-linearity, like the piezoelectric effect, shape memory alloys. Nowadays people are also trying to fabricate it out of SMA. So these are the things which are there. And then coupled physics, you have to couple it with electrical related, thermal related equations to get the effect. If you forget everything, what is really required is we have to focus on the resonance, whether it is sharp or wide or, you know, so all other parameters that we are talking about, the effect is to control that resonance peak. Okay, so how do we solve it? For example, these are the coupled field effects which are evident in these MEMS devices. So like a squeeze film, here you have interaction between structure and fluid, right? Then you have thermoelastic effect. So when structure deforms, there is a temperature gradient form, and then the thermal equation, you have to energy equation also you have to solve along with the elasticity equation. Then pull-in effect, you have to solve electrical and mechanical related equations. Stiction, this is what I was talking about. When it comes and there is a droplet, let us say, on the substrate, it will stick, right? Like this, and then you will have to solve equation with the structure with the capillary forces, in the presence of capillary forces. So these are some of the coupled field effects that are quite common in MEMS devices, and you will need to really understand it to solve it. Okay, so how do you model them? Okay, so modeling is a challenge. You have to go through elasticity equation. Okay, beam equation, Euler beam equation is one of the simplest form of this elasticity equation. Electrostatic equation, like Maxwell, and so you will have to solve them together so that you can see the electromechanical effect, right? And then if you want to find out damping effect, you have to again solve it, the Navier-Stokes or Boltzmann equation. Boltzmann equation is for the rarefied flow, which is the micro flows, and Navier-Stokes is for the continuum flow. So you will have to club it again with the structural related elasticity equation. Okay, similarly for temperature you will have to couple it with energy equation and then solve it. So this will be a thermoelastic equation, this will be coupled equation. So here you can just see that there are two different approaches for MEMS design. First, you have to solve coupled equations using different techniques such as FEM, BEM, FDM. Then you have to extract lumped parameters associated with different field and then solve them, solve the corresponding equation to get the quantities. So out of all this coupling, what you really need? M effective, K effective, C effective to find out omega, because omega is under root K effective by M effective. And quality factor 1 by 2 damping ratio, and damping ratio C by C by 2 under root Km. So if you are able to find C, Km out of all physics, you simply have to see how it is going to affect your performance parameter based on the resonance speed. Okay, this is the key in MEMS design. So every coupling, everything you need to really deal with that particular set. Okay. Okay, so how much time I have?
Sir, actually, we have planned for sessions for 1 hour and another half an hour for queries.
Okay, so shall I stop it here?
As you wish, sir.
Yeah, so I'm fine. I have. If you want me to talk more, I can talk more. And but here I can stop logically. Otherwise, again I'll go into different modes.
Yeah, okay, sir. That was actually a mind-blowing session because probably it would have become an eye-opener session for many of them who are attending this session. And we have
I hope so.
we have a question fire for you waiting.
Yes, please.
So you can have some water because there are so many questions.
No problem. No problem.
Okay, sir. Okay. Shall I start, sir?
Yeah, yeah.
Yes. Can you please share the current research topics in MEMS sensors?
Current research topic in MEMS sensor is one is your terahertz related thing, terahertz metamaterials. Okay. Second one is your MEMS devices like MEMS gyroscopes based on your ring type and disc type sensors, which are becoming popular now to improve its accuracy. The third one is array based, like unless you put them into array with the flexible electronics, it is not really going to really make sense for the bigger structures. So flexible electronics based on MEMS basically is another area which is going on, and optomechanical, optoelectronics, which is again a very key to the success of utilizing this IoT based thing, because IoT involves many sensors, and unless these sensors can be processed at a faster rate, it doesn't really make sense. So we look for opto electronics based devices where optomechanical cavity is being formed, and this also utilizes MEMS. Okay, so these are very broad area which are really in focus currently, and people are trying to explore it.
Okay, sir. Okay. Shall we move on to the next question, sir?
Yes.
Today, battery cars are famous.
Yeah.
Why can't we convert mechanical energy to electrical energy 100%? Why energy is lost? Can we sense energy loss in cars?
Oh yes. See, the energy losses there are different types of losses in cars basically. One is like this whole world doesn't really act independently. There are a lot of interaction which is happening. So for example, if the gear has to move, gear will interact. Now when the interaction happens, losses will happen. Now from where that loss will be taken care of. So that's how you have electrical. When you have a battery, it tries to provide the required energy that you design for, but at different drive trains, when you go into different components of drive trains, there are a lot of losses happening, so you can't really get the 100% output. So that is quite impossible, and it is against the principle of entropy also, right? Entropy always
Yes.
increases. It doesn't decrease.
Yes, sir. Uh, Another question, what will be the best simulation tool for designing MEMS sensors to characterize all the essential parameters?
So currently there are two, which is like a packaged one. One is your IntelliSuite, another one is Coventerware. Okay, so either one of them are fine. So for the beginner, it is quite useful. But let us say if you are trying to change, certain parameter for which the module doesn't exist in Coventerware or in IntelliSuite, then you will have to really do physics based analysis separately. Like you can use COMSOL, for doing uh, some changes that you want to include, but those modules may not be available in IntelliSuite or Coventerware. Okay, or
Okay.
using your MATLAB. So I would say that if there is some beginner who wants to do MEMS related design and analysis, for them IntelliSuite Coventerware works well.
Okay, sir. Working with flexible devices at high voltage is possible. What are the changes that are required for that?
So for like I'm first of all, I'm not an expert in flexible electronics, only in terms of MEMS I know. So MEMS usually requires low voltage, so I still have to explore it. I'm sure there must be some of the devices that might uh, require high voltage, but the thing is, the main purpose of going into the MEMS is that it should require low voltage. Okay, so if we are really looking for high voltage device, then why to go for the flexible electronics? We want to reduce the dependence on the power requirement and improve the performance of these devices. Okay, so I don't think there will be really too much of requirement of voltage. That's why people are also talking about you know self powered sensors based on energy harvesters and all. Unless you go and develop low powered MEMS devices, you can't really make it self powered using energy harvesters or all, right? So to answer your question, like I'm not really aware of what is the highest uh, voltage or more voltage required flexible devices, but from my understanding, uh, the focus is always to design low powered devices such that it requires low power and increase the efficiency. Okay, and
Okay, sir.
yeah, so this is what generally is being done.
Okay, and add to that question, what is the material used to make flexible electronics? What are its
Uh,
disadvantages?
so in flexible electronics, basically people use uh, like different types of gels and all. As I said, related with the fabrication also, I of flexible electronics, I'm not really very versed with. I'm mostly work in the silicon fabrication related. Okay, so you
Okay,
have,
sir.
let us say, two kind of the slides, and you make your devices, you just club them together, but the pressure has to be applied properly, and the wiring has to be taken out. So we used to use slides, right, for the presentation earlier. The people have also used those kind of material for flexible electronics.
Okay. Okay. And then
But there are a lot of literature available. You will get like all the information the moment you just try to Google flexible electronics microfabrication technique. Those things are all there. It's a very popular and vastly explored topic. Okay.
Yes, sir. Uh, the next question is, magnetic levitation trains are running amazingly.
Yeah,
Likewise, is there a possibility of cars in Industry 4.0?
maybe, maybe, yes.
Okay. How micro mirrors are working?
So the micro mirrors, as I said, they are actuators, right? So you have uh, this mirror, and through the middle you try to suspend it. For example, let us say you have a beam like this and they act like this. So this is the kind of motion. So what you do, you put here one electrode. Okay, here is one electrode, another electrode is here. So when you try to apply voltage between this and this, so the sinusoidal motion, so it will go like this and then go up, like this, go up, like this. Okay, so as you control half electrode and half side of your proof mass of the mirror, okay, so it will just move like this. So what will happen, let us say if the light is falling on the mirror, and if you want to deflect it in other direction, so the most voltage is applied here, so that you just turn it, so when light comes it will deflect in this direction, right? So since there are millions of micro mirrors, you can control the motion of all the mirrors in such a way that whatever light comes from the top, they all focused towards one side, and that way you can improve the resolution of the image also. Okay, so that is the principle behind the micro mirror operation.
Okay, that was wonderful. The next question is, what is the difference between optomechanical and lidar or lidar?
So lidar is optics work independently, radar works independently. Okay, so when you try to combine uh, laser optics with uh, radio signals, radio which is a radar, okay, so when you try to combine infrared related optics with radio signal which is radar, it will give you lidar. So the main significance of radar is it can travel for a long distance, and here you have a laser which is accurate, but it is accurate over a small distance. So the if you combine them such that it can create an ideal or a system which will accurate as low as or as good as the laser, and it can go for a long distance as long as the radar. So that's how the radar system came into picture. Now coming into your optomechanical related cavity, so there you don't have any radar. Okay, so what really happens, so let us say you have a MEMS device, okay, and when this is your fixed bottom, okay, and this is your moving MEMS structure. So now when I put a laser from the top, so some of the laser will pass through this structure, and it will form a cavity between them like this, okay, standing wave. So now when my structure moves, you can see that this, if this is your standing wave, it also moves like this, right? So it means it is interacting. This standing wave of the laser is interacting with the mechanical motion of your device. That's what we call it as a optomechanical coupling. Okay, and when this cavity is formed and it interacts the mechanical with the mechanical motion, it improves the signal. Okay, that resonance peak that you see, that becomes quite controllable. So a small change can be using this optomechanical effect, even the smallest change can be captured. That's why this optomechanical effect has become quite important in the present condition.
Okay, okay, sir. Is it possible to design a dissolved oxygen sensor and conductivity on a single MEMS sensor using COMSOL?
Using COMSOL?
Yes, sir.
I I didn't get your question. Can you please repeat again?
Yes, sir, sure. Is it possible to design a dissolved oxygen sensor?
Design and
Dissolved oxygen sensor.
dissolve.
Yes.
Acha, acha. Design and dissolve oxygen sensor.
Sir. And conductivity
Okay.
on a single MEMS sensor. Now, probably the question is to design a sensor which
Huh.
dissolve oxygen as well as conduct, I guess.
Dissolve oxygen and
Uh, the question is not clear.
oh, okay, 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 okay. Is it like dissociation of oxygen such that it becomes start conducting? This is what is like in the environment, uh, changing the conductivity of the surrounding. Is he talking about?
Probably, sir. Let us wait for that participant to ask once again. We'll move on to the next question.
Yes.
Can you suggest any books to read on MEMS?
Yeah, there is Centuria, SD Centuria book on micro system is there, which is quite fundamental in nature. And there is a handbook of micromechanical system by M. Bao, Minhang Bao. Okay, these two books are quite fundamental in nature. So it contain many. Then fabrication related books you can find by Mark Madow. This is a fundamental of microfabrication, nanofabrication, Mark Madow. Okay, these three books are enough to understand the deep understanding of MEMS design and fabrication.
Okay. Another question is why most of them are using cantilever? Can we use any other beams?
You can use any other beam, but the cantilever is the most simple design. Okay, so that's why people first start with most simple design. If they are successful in doing that, you can go for another typical. That's why you will see that nowadays you have fixed beam, you are having you might have I didn't really show you many of the like there are fixed beam also, there are star kind of, there are so one of the most like significant advantage of using cantilever is quite simple, and it has more flexibility, you know. So the moment you apply electric voltage, it just deflects. If you apply some pressure, it deflects. So it has more flexibility in nature. Okay, stiffness is of course low as compared to the more fixtures. Okay, so that is one reason why, you know, everything starts with cantilever is amazing, you know. You name one kind of device, you will see that it has, people start with cantilever. Simple to deal with, but lot of information to give. Okay.
Okay, sir. One of our participants has asked, being a mechanical engineer, I have decided to do actuator fabrication. For analysis, is ANSYS a suitable software?
Yes, in ANSYS you can do analysis. It has electromechanical module, it has electrothermal module, it has many modules there are, but even circuit related modules are there, but it doesn't have any fabrication related module. So that is the, it is complete, whatever multi-physics analysis you can do based on FEM, this is what ANSYS can offer you. And if you are not looking for any fabric, like to take the fabrication along with that, you can very well do it. Even I have done a lot of analysis using ANSYS.
Okay, sir. The next question is, what is the difference between testing of ICs in on MEMS devices?
I didn't get, what is the difference between
Testing of ICs and MEMS devices, sir.
testing of IC?
ICs.
I would, is it like testing of MEMS devices?
Probably, sir. The question is incomplete. Okay. We'll move on to the next question. Sir, any suggestion?
So I'll just give a little bit of, so testing means, so in IC basically we have mostly, you know, substrate and oxidized wafer which are static in nature. Okay, so we try to so so one IC is there where we are having fixed oxide layers and your silicon layer. Now when you come to the MEMS, there is a hanging structure. Okay, so the difference is that in this you have mostly static. This is IC related thing will be called static measurement. Okay, and in MEMS you have dynamic related measurement where the movement of mechanical component also comes into picture, and you look for the resonance uh, uh, change or resonance measurement also. But in IC you don't look for it. If it is there, it is electrical resonance that you look for, LCR.
Yeah. Okay, sir. Okay, sir, any suggestions for utility of terahertz electronics in the field of biomolecules? Can we imply it for sensing carbohydrates or lipids?
Oh, that is specific question I can't really give. I can't answer. But as I said, terahertz is basically you can use. You know, you can apply it to any application. The only focus here is you will be able to tune the electromagnetic property of the device. Okay, so let us say if you want to tune it, if you want to use, let us say, test the virus. Okay, so uh, I think you can use it because I've seen people making use of this optomechanical thing. So if, let us say, if you are putting a virus on the top and then you are passing through uh, uh, the light, so if because of that, if there is a change in the dielectric property because of the virus presence, so of course there will be further change in other quantity. So that way one can think of. But terahertz devices means this is a way you can tune these electromagnetic parameters, okay, very easily. Otherwise whatever device you fabricate, it has fixed electromagnetic parameters. But in the terahertz metamaterial, you can tune these parameters. Okay, this is the advantage. Now the application is open. Where you want to use it, it is completely open. Okay.
Okay, sir.
One of the application I said that if you want to make something stealth aircraft, right? People are working on stealth aircraft. So if you have the outer material of that aircraft made of metamaterial such that it can increase the losses and it becomes invisible. Okay, so that is one very good, very big application which is there. In bio also you have lot of, but I can't really tell you specifically if it can be really used for lipid test or some other test.
Yeah, okay, sir. And one last question, is it possible to simulate circular shaped diaphragm in IntelliSuite software?
Yes, yeah, you can.
Yes, sir.
It can be done in anything. You can do it in IntelliSuite, you can use it in ANSYS, you can use it in COMSOL, you can do it CointerWare. It's simplest diaphragm.
Okay.
Yeah.
One last participant would like to clear her doubts.
Ah.
Sri Manasa, you can raise your hand so that we can unmute you because we didn't understand the question properly. Om Sri Manasa, can you just raise your hand? Sri Manasa, you just give a hand raise so that you can ask the guest directly.
Hello, sir.
Yeah, hello.
Sir, actually, I would like to know if it is really possible to have a conductivity sensor to design on console and like two sensors like dissolved oxygen also. Like we are doing a final year project with conductivity and dissolved oxygen. So we want to do this as a single MEMS system. So is it really possible to simulate it in console?
Uh, so it's like you are saying it is a coupled uh, chemical and electrical module, right?
Yes, sir.
In COMSOL is quite good in doing this multi-physics coupling analysis. So as far as I know, I think you should be able to do it because battery related, it has a very good battery related module where all this chemical as well as thermal and structure related analysis can be done quite easily. So yes, you can do it in COMSOL.
Thank you, sir.
Yeah, thank you.
So that's it, sir. The, se-
Okay,
the
thank
session was very, very wonderful, and thank you so much for your patience to answer all the questions.
No problem. Thank you very much. It's my pleasure.
we
Nice
we are yeah
meeting to you all.
we are actually having a mixed set of crowd, which involves faculty
Okay.
members, research scholars, students of all sorts
Okay.
we have. So your
Okay.
session was so wonderful because you started off from the scratch and you explained each and everything like teaching a child. So probably I would have admired your session. So thank you so much.
Thank you. Thank you very much. Thank you very much, all of you.
Okay,
Bye.
sir. Thank you.
Bye.
Bye bye. Nancy? Yeah. You can end the session formally by giving them instructions. Participants, we have some instructions for you and a last poll to know about the session, the feedback of the session.
Dear
Nancy?
participants, yes, ma'am. Dear participants, thank you so much for the feedback which you have given for the previous sessions. Our ultimate aim is to bring the experts in MEMS field from all parts of the world to create a very good exposure to all of you with the insight across the globe. So actually, we gave an option for the guest speakers that they can send the pre-recorded videos uh, due to their busy schedule or due to different time zones. But from your inputs, we were able to identify that audio and video for the pre-recorded sessions quality has to be improved. Yes, definitely we will take your valuable suggestion and we will give the instructions clearly to the guest speakers regarding this. So regarding the simulation and practical sessions also, we have scheduled those in the forthcoming sessions. Hope you will all enjoy and learn a lot more by the forthcoming live sessions too. Yes, now we would like to know about today's session feedback. So we will launch a poll now. Please do your voting for the questions asked so that we will take up your valuable suggestions will help us to improve our upcoming sessions. So I'll launch a poll now. Just a moment. Yes. There are 4 questions being asked. You can please start voting for it.
Yeah, we can end the course, Nancy. Yes, results are the content of the day was useful and interesting. Yes, 62% have said it is excellent, and 33% is good, and 10% has voted for satisfied. Did the session improve your understanding of the topic? Yes, 100%. So thank you so much for that. Was there enough time for questions and discussions? Yes, we had. Luckily, our guest was so patient with us. And finally, how organized was the event? Extremely organized, 48%, and very organized, 48%. So with that positive note, uh, we are saying a formal thanks for today's session, and the quiz for today's is posted in the Zoom. It will very soon be posted in your WhatsApp as well as Telegram links too. Thank you so much.
So much. We thank all the participants for joining with us today. Hope you all have gained knowledge about MEMS sensors and have been benefited by the session. And most of the questions are also answered by our guest today. Our upcoming session is on MEMS sensor design by Dr. A.R. Kalayarisi, Associate Professor, Savita Engineering College, Chennai, scheduled on June 26th, tomorrow from 11 a.m. to 12:30 p.m. We request all the faculties and students to attend this session and get benefited. The link for today's quiz will be posted in the Zoom chat box and in our WhatsApp group. We request all the participants to kindly finish the quiz of today's session before 11 p.m. today. Learning never exhausts. We officially end our today's session. Enjoy the course and extend your fullest cooperation. Meet you all in our next session tomorrow. Thank you all for your participation. Stay safe. Thank you. Bye.
Nancy, we can close the session.
Bye.